All right. Hi, everyone. Can you hear me all right? So let me know in the chat, please, if you can't. So either I'm not checking the YouTube chat, I'm just checking the Discord and the Zoom chat. If you want to speak live, Miami, yes. If you want to speak live, then I suggest using the Zoom. Are there any complaints about the sound or anything like that? There is no in-person lecture today, as announced by email and in the previous lecture. You can, however, watch the stream or talk to me on Zoom. All right. Okay. So seeing no complaints, there is a quiz. So please go and do quiz number 7. So this is the quiz. So I'll let you think about it for a bit. We are pretending that this is an in-person lecture. So think about the quiz. All right. So, okay. So what's going on here? So in the task, what we have is a list like this. And what we're trying to do here is we're trying to find the index of the 15, right? So whatever it is, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I can check it like this. If I say that the list is here, L at 11 is actually the 20, so L at 10 would be the 15, right? So, all right, so I'm looking for that. And the way I could do it efficiently is by saying, well, I'll try the middle. So that's approximately this 4. And then I'm saying, is 15 on the left or is it on the right? Well, 15 is greater than 4 and the list is sorted. So that means that we're looking on the right. And then we're saying again, like, what's the middle? Well, about here. Is 15 on the left or on the right? The answer is on the right. So we will be looking over here. So that means that if we're looking for the 15, the sorted list using binary search, that means that we say, okay, it's in the second half. And then looking at, is it in the third quarter or is it in the fourth quarter? The answer is in the fourth quarter. So like in the second quarter of the second half. So this is the answer. Make sense? The answer to are you here? Well, it might be yes or it might be no, but if you're answering, then it's a yes. All right. Okay. So this is this. And now I want to go back and look at the implementation of this strategy. So this is kind of what it would look like, not kind of, exactly. So we're doing binary search. Our input is the list L, and we're looking for the element E. So the strategy is we're thinking of a list. This is the code from last time, right? So the strategy is we are thinking of a list, like maybe something like this. And we're looking for an element, so maybe the 10. Right? So what we're saying is we'll define the index low, and that is going to be initially 0. And we'll define the index high, and initially that's going to be the index of the last element. So the length of the list minus 1 because it starts with 0, right? So what we're saying is low is the lowest possible answer, and high is the highest possible answer. And initially, well, it could be as low as the location of the first element, 0. It could be as high as the location of the last element. And then what we're going to do is we're going to keep going until it's not the case that low is smaller than high. So when low is the same as high, that means that we found the answer, because if the lowest possible answer is the same as the highest possible answer, then the answer is just the lowest possible answer. All right. Okay, good. They're having fun. So, okay. So what is it that we're doing here? We're saying, let's look at the middle element. So that's the average between the low and the high. So initially, if low is 0, high is the location of this. Mid is going to be the average. Why the integer division? Well, because it has to be an index. So if low plus high happens to be odd, then we just round it. All right. So, okay. So now we're saying 3 possible things could happen. So it could be that L at mid is just equal to E. In that case, we have the answer. Like what we're looking for is the location of the E. If we know that L at mid is equal to E, that means that the answer is just mid. So we can just return it. If it's not equal, we can say, okay, well, what if L at mid is smaller than E? So L at mid is something like this. And if it's smaller than E, as is the case for E equals 10 and mid being the location of the 8, that means that the answer is definitely to the right of mid. So we update low to be mid plus 1. So that means that low is the location of the 9, and then high is still the location of the 11, and we're looking over here for the answer. The other possibility, if E had been smaller than 8, so if E had been, 1, for example, then it would be the other way. We would make high be the location to the left of mid, so this, and low would still be the same. So we'd be looking over here for the answer. And we keep going while low is smaller than high. If we're here, that must mean that low is not smaller than high. So that means that we know the answer. The answer is just low. Make sense? Okay, let's run it just the once. So let's say that we're looking for the 10. What is that going to look like? So initially, it's going to be that low is equal to 0, and high is the length of L. So the length of L is 7 minus 1, so 6. So we're saying, okay, so while low is smaller than high, so 0 is smaller than 6, mid is the average. So in this case, mid is 3. And we're saying, is L at 3, so this guy, equal to E, 10? No. Okay. Is L at mid smaller than E? In this case, yes. So that means that low gets updated to mid plus 1. So low now becomes 4. That's it. So we are looking in between L at 4, and L at 6. Okay. So is L at mid equal to, so mid now is going to be the average. So that means 5. And now we're saying, is L at mid equal to E? The answer happens to be yes. So we just return 5, which is what we want. Okay, there is a question in the chat. Why do we return low? And the answer is like we assume that it's present. Okay, so the question is, why do we return low if it's not present? Like we assume, like for the purposes of this one, we assume that the answer isn't there. If the answer is not in there, then you got to do a little bit more. So that's what's in the handout, which I'm about to discuss. Okay. So let me just repeat what I said before about the analysis of how fast is this, right? So yeah, I know the laptop may die after 25 minutes, and that might be the end of the lecture. Exciting. I'll dim my screen a little bit so that you get more of the lecture. Well, now I can see. So, okay. So, by the way, just an estimate. So, okay. So let's say that the length of L is N. So one question to ask is how many iterations of the loop? So that's what we kind of did before as well, but I want to repeat it now. So how many iterations of the loop does it take to get the answer? Well, so we are going to do it kind of approximately. So high minus low is the size of the range of indices that we're looking at, right? And high minus low decreases by at least a factor of 2 every iteration, right? So why do I say at least? Well, because we are actually making it usually a little bit smaller than the previous high minus low over 2, right? Because approximately what we're doing is we're throwing half the range away, but actually more than that, right? Because we're saying, well, let's look at the middle and then throw away the middle and just look here. So high minus low, in this instance went from 7 elements to 3 elements. All right. So in this case, high minus low like used to be 6 minus 0, and now it's 6 minus 4. Right? So it's more than a factor of 2, but at least a factor of 2, because high minus low is a largest the list that we're looking at. Okay. So what does that mean? It means that for iteration 1, high minus low is approximately n. And then for iteration 2, high minus low is smaller, I'm going to say approximately, than n over 2. So like strictly speaking, it's like smaller or equal because we're decreasing by a factor of 2 and a little bit more. So it's smaller than n over 2. And then iteration 3, it's smaller or equal than n over 4. And then iteration 4, it's smaller or equal than n over 8. And so on. And at iteration k, we're done. So the question, again, kind of that we're asking is, how many iterations does it take to be done? So essentially, what is k? And the answer is, again, if we go from the bottom to the top, so if we go 1 and then 2 and then 4 and then 8 and so on up to n, which is equal to 2 to the k for some k. and we're asking what is k, the answer is k is approximately log 2n. Why? Because that's what log means, is how many times do you need to multiply by 2 in order to get to n? Like that's what log is, right? So how many steps to get to n if you multiply by 2 every time? Log 2n. That is what log is. Other questions about this? So I'll check the Discord. I think the all is good is about something else. So, okay. So that is the answer to how many iterations. So why does how many iterations make sense as a question to ask? Well, because what we can say is, okay, I don't know how long it takes for any individual computer to run this iteration, this block of code. But I can say that it's some kind of constant, right? So maybe my computer is more expensive than yours or the other way. And that means that on mine or yours, it's going to take longer. But I can say, okay, like whatever it takes to run this, I can now say binary search for a list of size n requires at most log 2n times c, where c is a constant, right? So what this means is that on any particular computer, I can figure out what the c is. So it's however long it takes to run one iteration. And then I can say that the runtime as a whole is going to be proportional to log 2n. All right. So let's remember this and switch to analyzing something simpler for a second in order to really see the difference. So let's talk about just what's called linear search. So this is something that we've done many times. It doesn't take, much thinking. This is just looking through the list. So like, for I in range length of L, if L at I is equal to E, then return. So we can ask, how many iterations does this take? And the answer is, in the worst case, when E is at L at -1, it takes time proportional to T2 times n, where n is length of L. Yes, there is a question in here. So since n is high minus low, well, n is initially high minus low, right? And then high minus low becomes, high minus low becomes something different. So like I want to think about high and low as like local variables that I don't know about. So I'm asking, if I have a list of size n, how long is it going to take essentially? Make sense? So high minus low are kind of like, yes, like if you define low as 0 and high as n-1, then yeah, but those are local variables. All right, someone's typing another question in the chat. Okay. All right. So this is like this. And to come back to what I was saying before. So again, how many iterations does this take? Well, it could take as many as n iterations. So that means that running this is going to take time that's proportional to C2 times n. Okay, so let's put some kind of made up numbers on this just to see what's going on. So imagine that it's like this. Imagine that C2 is much smaller. And you might imagine that this is like maybe a little bit faster than this. Certainly this looks like more code. It's not like this exactly, but imagine that it were like this, right? So what's going to happen in this kind of situation? Well, if I have, let's say, 5 million, and so if I have like 50 integers, well, 0.001 times 50 is going to be like this. And then binary search. So put units on there like they probably tell you in physics. So binary search is going to be 0.00, supposed to be like this. That's like this. And then 0.001 times log 250. So I don't know off the top of my head how much is log 250, but that's okay because I have log 2 over here. And I can multiply it by this much. That's going to be actually about the same already. For length of L equals to, let's say, 50 million, well, linear search is going to be, again, yeah, I mean, like this is just so the question is like, if is like C smaller than C2 because of different length? Yeah, like essentially like different number of operations that you do. Okay. So those are, of course, kind of made up numbers. This is just kind of for the sake of the argument. So linear search is going to be, this much. So 0.0001 times 56. So 5,000 milliseconds. So 5 seconds, right? But binary search is going to be 0.001 times log 2, 50 million. And log 2, 50 million is not very much. So that's going to be 0.02 milliseconds. So you see that what those constants are doesn't matter nearly as much as how much you scale with the size of the index. So because log of n grows so much more slowly than n, what you get is what's really important is the log factor, not so much the amount of time that it takes to do one iteration. So for that reason, because really what we care about is the factor that changes. So is it C2 times n or C2 times log n? That what we say is what is the runtime proportional to, in the worst case. Make sense? So what I mean by in the worst case is it might be that you return right away here. But what I'm really interested in is what's going to happen when things go bad. Okay, there is a question. Oh, it's a completely, again, why is C2? Well, there's no C1, there's just C. So this is hypothetical, right? So you might say that this is like less code, so maybe it iteration takes a small amount of time. Those numbers are made up. We can also measure them literally. In fact, let's do that now so that people are not confused. So we have binary search and we have linear search. So we can ask, sorry, let's not do that because I feel like this lecture is about to end. So, yeah. So, so when the lecture ends, it ends. Yeah. Okay. So sorry about that. I think the lecture is over. I will see everyone on I will see everyone on Monday. So okay, please. Yeah. Enjoy the rest of your day.